Okay, now let us solve question number 10. Maximize z equal to x plus y subject to the constraints x minus y less than equal to minus 1 and minus x plus y less than equal to 0. Subject to the constraints x and y greater than equal to 0. These are the non-negative conditions. Let us try to get the equalities corresponding to each of these inequations. So I write equality corresponding to x minus y less than equal to minus 1 is x minus y is equal to minus 1. We talked about the intercepts of this line. If you put y is equal to 0, value of x is minus 1. So the x-intercept is minus 1. If you put x equal to 0, it is minus y is equal to minus 1. So y is equal to 1. So here the x-intercept is minus 1 and the y-intercept is 1. So when y is 0, x is minus 1, and when x is 0, y is 1. The other inequality. So equality corresponding to minus x plus y less than or equal to 0 is minus x plus y is equal to 0. If I multiply by minus 1 on both sides, so what happens? X minus y is equal to 0. What you can find here is that these two equations, they are parallel lines. They represent parallel line. For this one, the x-intercept is minus 1, the y-intercept is plus 1, and for this line, parallel to the line represented by equation 1, it passes through origin. So it is a line y is equal to x. They are not going to intersect. Let us try to draw the graph. We have to respect the non-negative condition, x greater than equal to 0 and y greater than equal to 0. The x-axis and the y-axis, 1, 2, 1, 2, minus 1, minus 2, minus 1, minus 2. So for this one, the x-intercept is minus 1 and the y-intercept is plus 1. So we join these 2 points, so we get the line. So this is the line, x minus y is equal to minus 1. We are talking about the inequality x minus y less than or equal to minus 1. This point is minus 1 comma 0 and this point is 0 comma 1. The visible region corresponding to this inequality is a half plane of the line, either this half plane or that half plane. See, we decide at this point the x coordinate is minus 1 and the y coordinate is 0. We put y is equal to 0. So x is less than equal to minus 1. So at this point x will be less than equal to minus 1. X moves in this direction. So this is the half plane, that is the visible region corresponding to this inequality. Let us set them using the waves. Now we talk about the other one, x minus y is equal to 0, a line parallel to this line but passing through origin. So this is the line. It is minus x plus y less than or equal to 0. This point is origin Now, at x equal to 0, y is less than equal to 0. So at this point origin, when x is 0, y will be less than equal to 0. So y tends downwards. So this is the half plane corresponding to this inequality. So let us set it using dotted lines. Now we talk about the feasible solution region for this linear programming problem. So it is a region consisting of both the kinds of shading. We use two kinds of shading, the waves and the dotted lines. So the region in which you can find both of these kind of shading is a feasible region for this linear programming problem. As you can see, the waves are on this half side of line and the dotted lines on this. So they don't have a common shading region. So we show that for this linear programming problem, we don't have any feasible solution region. So that's enough. So I write feasible solution region does not exist. So in exercise 12.1, we have solved this linear programming problem. The linear programming problem was already available to us and we solved them graphically. We got the feasible region. In each of these questions that we have solved, we first get the feasible solution region, then we select the corner points, find the value of objective functions, and if it is demanded maximize, then we select the maximum value. If it is demanded minimize, we select the minimum value. Now in the next questions, we will be understanding how to solve the problems of linear programming on daily basis. There are many various kinds of daily requirements: manufacturing, transportation, diet related. So there are many daily needs applications that needs to be solved using the problem of linear programming, wherein we will have to first read the question thoroughly, and first we will have to formalize the linear programming problem. Once we have done that, we have to solve this graphically. That we'll see in the next lecture. Thank you.